Hello everyone, my name is Damjan Vukcevic. Today I will talk to you about Dawid-Skene models, which are used for analyzing data of repeated categorical ratings. What does this mean? Well, you'll see an example in a minute. First, to introduce myself, I work at the University of Melbourne as a senior lecturer. I have projects in several areas. Mainly I focus on statistical genomics, but today's work actually comes from a project to do with medical imaging. My collaborators on this project are Pullin and Lyle. Jeffrey is a master's student here at the University of Melbourne, and Lyle is a professor in biostatistics at the Melbourne School of Population and Global Health, also here at the University of Melbourne. So, what are repeated categorical ratings? Let's go through an example to see. So in this example, we're going to work with images such as this one. This is an image of someone's skin zoomed up, and what we see is a pattern of grooves and ridges. And we can classify this into different categories of different types of skin texture. So here is a categorization scheme that's well known by experts in this field. So the task is, given an image, which category does it belong to? And this is done by trained experts who understand this scheme. And they'll look at an image like this and say, this looks like it's in category 2 or category 3 or whatever category they think it is. Now we can do this multiple times, either by different experts, so different raters as we call it, or even by the same rater multiple times on different occasions. And what we find is, even when we have the same rater rating the same image, we can get different answers. So this task is not an easy one, and it by no means get perfect ratings. So here's a sort of data set we might get. So for each image, we get a series of ratings by one or more raters, including multiple ratings by the same rater potentially. And we see that we can get quite a bit of variation in the ratings. So not always, sometimes we get consistent ratings, sometimes we get inconsistent ratings. So the idea is now to use all of these data to come up with good answers to questions such as, what is the actual true class of each image? So can we get a more accurate assessment by using these multiple ratings as opposed to just a single one? And also, can we infer the accuracy of each rater? And in particular, can we figure out, for example, if there's systematic biases for some raters, and then account for that in assessing what the true class is? So we can do all those things through the Dawid-Skene model. This is a popular model used for these sorts of data. And the sort of answers we'll get at the other end in this form. So for the classes for each image, so for each item, we will get a probability distribution on what we think the truth is. So here that's represented on the right in these columns. That's the probability distribution for each item. So here, where we have a single rating only, we end up with a probability distribution like this, where we're not, we think it's a 3, a class 3 in this case, which corresponds to the given rating, but we're not completely certain. There's a substantial amount of probability on the other possibilities in this case, especially probability 2, and a few more on the other ones. Where we have more data, so multiple ratings, we can get much more certain estimates. So we get tighter, more concentrated probability distributions. So here, where all the ratings are a 3, we're fairly certain it's a 3. We have high probability it's a 3. Here, where we have other ratings, a lot of ratings, but variability, again, is enough data to come up with a fairly certain estimate of what the true class is. So that's one format for answering the question of what's the true underlying class. We'll end up with an output from the model like this. We could use the probability distribution directly, or we could end up with what we call a hard call or a hard prediction by taking the class with the highest probability and submitting that as the prediction. So in this case, we'll take category 3 and say we predict 3. We could predict a 2 in this case, and for these two, we predict a 3. So a lot of the talk will be working with these so-called hard predictions. For looking at assessing the accuracy of the raters, here's how we would represent that. We call this an accuracy matrix, similar to a confusion matrix. where the true classes are in the rows and the observed classes, or the ratings, the rated classes, are in the columns. And each row here represents a probability distribution for how a particular rater gives their ratings. So if the truth is that it's a class 1, then in this case, they give 79% of the time a rating of 1, so an accurate rating. And the rest of the time, the 21%, is spread out across the other classes according to this probability distribution. And similarly, for each other row corresponds to a different other true class. So if a rater is rating accurately, what we expect to see is high probabilities along the diagonal of this matrix. And the entries off the diagonal represent errors, so errors in the rating. And we can get different patterns of mistakes by putting the probabilities in different places. So in assessing the accuracy of the raters, we'll end up with estimates of this sort of accuracy matrix separately for each rater. So the model that lets us do this is the Dawid-Skene model. Now, I won't go through all the mathematical details of how this model is specified. The key point is that those accuracy matrices are a key aspect. Each entry in the matrix is a parameter. So we have a separate parameter for every entry in every matrix, so for each rater. So that's a lot of parameters to estimate, and those are the ones that are the bulk of the parameters in the model. And so we'll end up with a posterior distribution of what those look like. In addition, we have the latent variables, which are the true classes for each item. We'll end up with a probability distribution on those ones. So those are the two key outputs of the model, and those are the main things you need to know about the model, other than it's a fairly straightforward set of categorical distributions put together with Dirichlet priors on them. So if you're familiar with a multinomial Dirichlet model, it's a similar sort of idea, except that there's some latent classes involved. So this model is actually used as an example in the STAN manual. And what we've done is we've taken that and many other variations and implemented it as an R package called Rater. So you can check that out on Jeffrey's GitHub page. There's the URL. And you won't be surprised to know that we use STAN under the hood for implementing all of the models. Just to give you a snapshot of what the output looks like in R from that package, here is a visualization of the latent class distributions. So each row here is a separate item. And here's a visualization of the point estimates of the accuracy matrices. So here we have 3 raters matrices, and what we see is sort of nice high values along the diagonal. So now they've got the background, I'll give you an overview of the rest of the talk. I had intended to talk about a few different things, but I'll only have time in this 20-minute video to just talk about one thing in detail. So that's all I'll attempt to do. And that is a comparison of the Dawid-Skene model against some simpler alternatives. So the motivation here for us was to understand how well the Dawid-Skene model works, when it works well, when it doesn't, and to offer some recommendations for use. So what I'm going to show you today are just some highlights from our explorations. And indeed, all of the other aspects came about from a similar motivation, but I'm not going to have time to cover some of those things. For the results I'll show you, they're based on simulated data, so where we know the latent class, so that allows us to assess accuracy. So these simulations are based on various choices for how many items and so forth. The main thing to note is that we've assumed an accuracy of 0.7 for our raters. And when they make an error, we assume that this is uniformly spread across all of the other categories. There's various ways to measure performance, which relate back to the questions that we started with. So if we're interested in predicting the latent class, we could just take the hard predictions and assess how accurate those are, so what proportion of those are correct. Or we could work with the probability distribution and assess that in some way, something that's usually known as calibration. We won't do that in this talk, but I wanted to highlight that's something that's possible. We could also look at how well we infer the accuracy of each rater. So in other words, the estimates of those accuracy matrices. Again, it's something we're not going to tackle here, but it's something that is of interest. So for the analysis in this talk, we'll only look at a prediction of the latent class through hard calls. So the first section, let's look at the Dawid-Skene model and compare it to other approaches. And the first one I want to think about is, what would someone do if they didn't really know any statistics at all? How would they use these data? So they would probably do something that we call majority vote, which is look at all the ratings they have and pick the most common one. And if it happens that the most common one is a tie, well, we can just pick one at random. Fairly straightforward, fairly easy to explain, easy to implement. How does that do compared to Dawid-Skene? Well, if we assess it using our simulations and using just the accuracy of the hard calls, it does remarkably well. In fact, it does better than the Dawid-Skene model. So here, on average, we're getting about 90% correct with majority vote, and about 86% on average correct with the Dawid-Skene model. So when we saw this, we were a bit surprised, because the Dawid-Skene model is analyzing all the data together jointly in the right way, using a proper model, and doing things like correcting for any error, any systematic biases, any raters and so forth. We thought, how could it possibly do worse than something as naive as majority vote? And the answer, it turns out, is that it's doing a bit too much. So for this question, you don't need to go do as much hard work as the Dawid-Skene model is going to. It's enough, the majority vote is sort of capturing enough of the information in a fairly straightforward way. And to see that that's indeed what's happening, that somehow the Dawid-Skene model is paying a penalty for trying to estimate too much, we can define some simpler models and compare it against those. So we'll define this model called the class-conditional Dawid-Skene model. So this is just the Dawid-Skene model, but with a restriction. We're going to assume uniform the matrices off the diagonal in the accuracy matrices. So that means we'll reduce the number of parameters rather than having every entry as a separate parameter. Off the diagonal, they're all going to be the same parameter on a per row basis. So there's many fewer parameters to estimate here. So this is going to be doing something closer to what majority vote's doing, in that it's not caring so much about any specific biases. And there's another reference point. We're going to use what we call the oracle Dawid-Skene model. This is just the Dawid-Skene model, but where we set the parameters to their known values. So that means we're not in estimating them. So we don't need to have pay any penalty for estimating the parameters. So there will be no uncertainty due to estimation. We will still assume the latent classes are not known, so only the other parameters. So that means the only uncertainty left is to do with inferring the latent class. So this model will give us essentially an upper bound on the possible performance we can get from an actual real model in practice. So here was what we get when we put all of those models side by side. So the middle two are the ones we saw before. Class-conditional model on the left, we can see is now matching the performance of majority vote, and we can see that it's on average it's the best possible because it's equal to the performance of the oracle. So this comparison on the left between the class-conditional model and the full Dawid-Skene model shows you that actually this penalty is indeed to do with estimating those extra parameters in the accuracy matrices. If we didn't have to do those, we don't pay that performance penalty. So that's gives us the right, so we can see that that's how to interpret this penalty. Now, does that mean we don't need this full model? Is it enough just to use majority vote? Well, in this simulation, the assumptions in the class-conditional model are exactly what we've used in the simulation, that there's no systematic biases for any of the raters. Suppose there were, will then Dawid-Skene have the edge? Will it have a performance boost? So we explored that through simulation where we made some of the raters give meaningless ratings. So we've what we call spammers. So instead of giving a rating that depends on the true class, they're just going to give a rating of 3 instead, and otherwise equally, so that's 0.7 of the time, rather than giving an answer that's true 0.7 of the time. And for the rest of the 0.3, we're just going to spread out the ratings across the other categories as before. So if our raters are spammers rather than accurate raters, we'll be introducing noise into the data. How will the models cope? So we're going to explore changing some or all of the raters to be spammers and see what happens. On the right here, we have the scenario before, no spammers, every rater is an accurate rater. On the left here is every rater is a spammer. And in the middle, we gradually increase the number of non-spamming raters. So we have 1 informative rater, 2, 3, 4, up until we have all of them. So let's see, on the right, we have the performance results you saw before. So we understand those. On the left, this is the scenario where everyone is a spammer. So that means there's no informative ratings at all. Everything is noise. And unsurprisingly, all the models are performing the same. They're all essentially guessing, and you can't do any better than just guessing. So they're all the same. Once you have 1 informative rater, well, the oracle knows the truth, knows which rater it is, so it can make use of their ratings, and it gets quite a lot of performance boosts compared to the previous scenario, simply because it can ignore all the noise and just base its performance on the accurate rater. The other models don't really have enough information to pick up on that signal. The majority of it's picking it up slightly, but not very much. Once we have 2, we can see the models are starting to pick up on it. So you can see majority of Dawid-Skene getting higher performance. And once we have 3 out of 5 are informative raters, this is the point at which we have the majority of the raters are giving actually informative ratings. We can see now we're doing much better. And in this case, the Dawid-Skene model has indeed managed to perform better than the others because it is able to infer the systematic errors that the spammers are giving and discount them accordingly in a way that the class-conditional model cannot. So you can see here that the class-conditional model, the restriction imposed on it, is hampering its ability to get the signal. So this stark difference is due to the fact that the extra work that Dawid-Skene model is doing is actually paying dividends here. It's able to account for the biases in the right way. And indeed, it has the edge over majority vote, which isn't able to do any such sophisticated modeling. It's just doing it in the ad hoc manner that through just the majority voting mechanism. And then by the time we have 4 out of 5 raters being informative, most of the approaches are able to pick out the signal. So they're all getting similar performance. The Dawid-Skene models being just slightly ahead. And by the time we have no spammers at all, we're in the scenario as before, where the Dawid-Skene model is paying that slight penalty for having that extra robustness. But otherwise, the performance is fairly similar. So we can see that that penalty we're paying here, the small one, is just small. But here, when we are in an environment where there's a lot of noise, that penalty is actually a strength and gives us a lot of robustness in a way that the non-robust models, like the class-conditional ones, do not have. So we can indeed see that performance does make sense. So this, what turned out to be a surprising difference here, makes sense in that it's just a small penalty for gaining robustness. To summarize what we've talked about today, we've looked at data that from repeated categorical ratings, and we've explored and analyzing these using Dawid-Skene models and some variants. What we found is if we're interested only in hard calls after latent classes, it's enough to do something simple, often like majority vote. And I didn't talk about optimization versus MCMC, but a similar conclusion applies there. If you want to go beyond this, looking at probabilistic outputs or inferring the accuracy of the raters, you really need to apply a full Bayesian inference using the Dawid-Skene model, which you can do so straightforwardly using our rater package in R. I didn't get around to telling you the details about the ratings per item, but I can tell you the broad conclusion from our analysis there is that you really want to try to get at least 3 ratings per item to get good prediction accuracy. Thank you very much.